Imagine you want to share a secret with someone you have never met, but there is a catch. A spy is listening to every single word you say. How can the two of you agree on a secret code without the spy hearing the code itself? This is the fundamental paradox of secure communication. Historically, we have relied on what are called symmetric cryptosystems. In this model, two parties, let's call them Alice and Bob, share a single secret key, which we will denote as K. When Alice wants to send a message M, she uses an encryption algorithm, ENC, combined with this shared key K to produce a ciphertext C. Bob receives this ciphertext and uses a corresponding decryption algorithm, DEC, with the exact same key K to recover the original message M. We call this system symmetric for two main reasons. First, the same key is used for both encryption and decryption. Second, the mathematical functions for encrypting and decrypting are often very similar. In some cases, like the Data Encryption Standard, or DS, they are even identical. You can think of this like a physical safe with a very secure lock. Only Alice and Bob have a copy of the key. Alice puts her message in the safe and locks it. Bob uses his key to open the safe and read the message. While this works beautifully in theory, it faces a massive practical hurdle often called the key distribution problem. If Alice and Bob have never met, how do they get that shared key in the first place? They would need a secure channel to exchange the key, but if they already had a secure channel, they wouldn't need the encryption to begin with. It is a classic catch-22. Beyond the distribution problem, there is the issue of scale. In a symmetric network, every unique pair of users needs their own unique key. If you have a network of n users, the number of distinct keys required is given by the formula n times n minus 1, all divided by 2. To see why this is a problem, consider a medium-sized company with 2,000 employees. For every person to be able to talk privately to every other person, over 4 million keys would need to be generated, securely transported, and stored. Each individual user would be responsible for securely managing 1,999 different keys. To solve these weaknesses, researchers Diffie-Hellman and Merkle proposed a revolutionary alternative, asymmetric or public key cryptography. The core insight is that the key used to lock the message doesn't actually need to be the same as the key used to unlock it. In an asymmetric system, Bob doesn't share a secret key with Alice. Instead, he generates a key pair, a public key, kpub, and a private key, kp. Bob publishes his public key for the whole world to see. Anyone, including Alice or even the spy, can use this public key to encrypt a message. However, the system is designed so that only the corresponding private key, which Bob keeps strictly secret, can decrypt that message. Let's trace this new protocol. Bob first sends his public key, kpub, to Alice. Alice then computes the ciphertext C by applying the encryption function to her message M using that public key. She sends the ciphertext C back to Bob. Finally, Bob recovers the message M by applying the decryption function to the ciphertext using his private key, kp. A perfect analogy for this is a standard mailbox. Anyone, including a stranger, can walk up to the box and drop a letter through the slot. This is like encrypting with a public key. But once the letter is inside, only the mail carrier with the specific private key can open the back of the box and retrieve the letters. To make this work mathematically, we rely on what are called trapdoor functions. A trapdoor function f is a one-way function with a special property. First, calculating the output c equals f of m must be computationally easy. Second, reversing the process to find m from c must be computationally difficult for anyone except for someone who possesses a specific piece of special information. We call this function f a trapdoor function because, like a physical trapdoor, it is easy to fall through in one direction but nearly impossible to climb back up unless you have the secret key to open it from the other side. This mathematical asymmetry is what allows us to communicate securely across an insecure world. Secure communication often relies on a shift in perspective, focusing on the remainder of a division rather than the result. This begins with the concept of divisibility. In this case, the division is clean. There is no remainder. However, in the world of modular arithmetic, we are specifically interested in the cases where a remainder exists. The modulo operation, written as a mod n, returns exactly that, the remainder of the Euclidean division of a by n. If we divide 17 by 5, the quotient is 3 and the remainder is 2. Thus, 17 mod 5 equals 2. This leads us to the concept of modular congruence. We say that two numbers, a and b, are congruent modulo n, written with a triple bar, if they leave the same remainder when divided by n. Formally, this means n must divide the difference between a and b. Looking back at our example, 17 is congruent to 2 modulo 5 because 5 divides the difference, 15, which is 5 times 3. We can also express this as 17 equals 5 times 3 plus 2. This modular world is contained within a specific set called Zn, which consists of all possible remainders for a given divisor, ranging from 0 up to n minus 1. To perform complex calculations, we rely on three fundamental identities that allow us to distribute the modulo operation. First, for addition, the sum of two numbers modulo n is the same as taking the modulo of each number individually, adding them, and taking the modulo again. Second, the same distributive property applies to multiplication. The product of two numbers modulo n is equivalent to the product of their individual remainders modulo n. Finally, for exponentiation, a raised to the power b modulo n is the same as taking a modulo n first, then raising that remainder to the power b. These identities are computationally vital. They allow us to keep our numbers small and manageable by applying the modulo at every intermediate step of a calculation rather than waiting until the very end to deal with a massive result. Consider the operation of division. In the familiar world of real numbers, dividing by 3 is the same as multiplying by 1/3. However, when we work within the set of integers modulo n, fractions like 1/3 do not exist. We are confined to the discrete set of remainders from 0 to n minus 1. This constraint leads to a fundamental question. Can we perform an operation equivalent to division in modular arithmetic? The answer lies in the concept of the modular inverse. Instead of dividing by a number x, we look for another integer y that, when multiplied by x, results in a remainder of 1. Formally, we say that the number y is the inverse of x modulo n if the product x times y is congruent to 1 modulo n. In mathematical notation, this relationship is expressed as x dot y is congruent to 1 mod n. When such a y exists, we can write it as y is congruent to x to the negative 1 modulo n. This notation mirrors the reciprocal in standard algebra, but it is important to remember that x to the negative 1 is not a fraction. It is a specific integer within our set Zn. The ability to find this inverse is what allows us to solve linear congruences and perform complex cryptographic operations. But a major hurdle remains. Does every number have an inverse? Unlike the real numbers, where every non-zero value has a reciprocal, modular arithmetic is much more restrictive. There is a precise criterion for the existence of a modular inverse. A number x possesses an inverse modulo n if and only if the greatest common divisor of x and n is equal to 1. In other words, x and n must be coprime. If they share any common factor larger than 1, the equation x times y equals 1 plus some multiple of n can never be satisfied. To understand why this condition is both necessary and sufficient, we can examine the logical steps that connect modular congruences to basic integer equations. We start with the statement that x possesses an inverse modulo n. By our definition, this is equivalent to saying there exists an integer y such that x times y is congruent to 1 modulo n. Now, recall the definition of congruence. Saying two numbers are congruent modulo n means their difference is divisible by n. Therefore, our condition is equivalent to saying there exists an integer y such that the quantity x times y minus 1 is divisible by n. If a number is divisible by n, it must be some integer multiple of n. This allows us to transition from the language of modular arithmetic into the language of standard algebraic equations. We can state that there exist integers y and k such that x times y minus 1 equals n times k. With a simple rearrangement of terms, we arrive at a powerful expression. There exist integers y and k such that x times y minus n times k equals 1. This specific form is known as a linear combination of x and n. This brings us to a cornerstone of number theory, Bezout's identity. This theorem states that for any two integers x and n, the smallest positive integer that can be written in the form x times y plus n times k is their greatest common divisor. In our derivation, we found that this linear combination equals 1. Since 1 is the smallest possible positive integer, it follows directly from Bezout's theorem that the greatest common divisor of x and n must be 1. The integers y and k are known as the Bezout coefficients. This logical chain provides the theoretical guarantee for the existence of an inverse. If the greatest common divisor is 1, the theorem ensures that such coefficients y and k exist, and therefore the inverse y exists. Conversely, if the greatest common divisor is not 1, no such integers can ever be found, and the number x is effectively non-invertible in that modulus. It is also important to note that when this inverse exists, it is unique within the set Zn. While there are infinitely many integers that satisfy the congruence, there is only one value between 0 and n-1 that acts as the inverse. This uniqueness is crucial for the consistency of modular operations, ensuring that when we divide by multiplying by the inverse, we always arrive at a single, well-defined result. The fundamental challenge in modular arithmetic is not just knowing that an inverse exists, but actually computing it efficiently, especially when dealing with the large numbers required for modern security protocols. To bridge the gap between theoretical existence and practical application, we use the extended Euclidean algorithm. This process is divided into two phases, a forward pass to find the greatest common divisor, and a backward pass to find the specific coefficients that satisfy Bezout's identity. Let's walk through a concrete example, finding the inverse of 17 modulo 59. We begin with the standard Euclidean algorithm to determine the greatest common divisor of our number, 17, and our modulus, 59. In our first step, we perform Euclidean division on the modulus by our number. We find that 59 divided by 17 gives a quotient of 3 and a remainder of 8. We express this as the equation 59 equals 3 times 17 plus 8. In the second step, we shift our focus to the previous divisor and the previous remainder. We divide 17 by 8, which gives a quotient of 2 and a remainder of 1. Algebraically, this is 17 equals 2 times 8 plus 1. For the third step, we continue this pattern, dividing 8 by 1. This results in a quotient of 8 and a remainder of 0, represented as 8 equals 8 times 1 plus 0. Since the last non-zero remainder we encountered was 1, we have formally proven that the greatest common divisor of 17 and 59 is indeed 1. This confirmation is vital. It guarantees that 17 possesses a unique inverse modulo 59. Now we move to the second phase, the extended Euclidean algorithm, often referred to as remounting or back substitution. The goal here is to express the number 1 as a linear combination of our original values, 17 and 59. In step 4, we start with our second-to-last equation, 17 equals 2 times 8 plus 1, and isolate the remainder 1. This gives us 1 equals 17 minus 2 times 8. In step 5, we look back at our first division equation, 59 equals 3 times 17 plus 8, and isolate the remainder 8 to get 8 equals 59 minus 3 times 17. We then substitute this entire expression for 8 into our equation from step 4. This yields 1 equals 17 minus 2 times the quantity 59 minus 3 times 17. Finally, in step 6, we simplify this expression using basic algebra. Distributing the negative 2 gives us 1 equals 17 minus 2 times 59 plus 6 times 17. By grouping the terms involving 17, we arrive at the final linear combination. 1 equals 7 times 17 minus 2 times 59. This equation is exactly what we need. When we look at this identity through the lens of modulo 59, the term minus 2 times 59 becomes 0, because any multiple of the modulus is congruent to 0. This leaves us with the congruence. 7 times 17 is congruent to 1 modulo 59. Therefore, the modular inverse of 17 modulo 59 is 7. We can easily verify this result. 7 times 17 equals 119. Dividing 119 by 59 gives a quotient of 2 and a remainder of 1, confirming that 119 is indeed congruent to 1 modulo 59. This specific inverse is unique within the set of remainders from 0 to 58, providing the precise mathematical tool needed for further cryptographic operations. RSA is the most famous public key cryptosystem based on the integer factorization problem. Invented in 1977 by Ron Rivest, Adi Shamir, and Leonard Adelman, its security is rooted in a simple but powerful asymmetry. While it is computationally trivial to multiply two large prime numbers together, it is extremely difficult to factor the resulting product back into its original primes. To understand how RSA functions, we must examine the procedure for key generation, which involves 5 critical steps. The process begins with a selection of two very large, distinct prime numbers, which we label P and Q. In a practical setting, these primes are chosen to be hundreds or even thousands of bits long. The second step is to compute the modulus, n, by multiplying P and Q together. This value n is made public and defines the size of the numerical space. The third step involves calculating Euler's totient function, phi of n. For a modulus n that is the product of two primes, this totient is simply the product of p minus 1 and q minus 1. This is a secret value that only the key generator knows. In the fourth step, we choose a public exponent, e. This integer must be co-prime to phi of n, meaning their greatest common divisor is exactly 1. This ensures that e has a unique modular inverse. Finally, the fifth step is to calculate the private exponent, d, which is the modular inverse of e modulo phi of n. This means we find a value d such that e times d is congruent to 1 modulo phi of n. Once these steps are complete, the keys are formally defined. The public key consists of the pair n and e, while the private key consists of the pair n and d. With these keys in hand, we can define the encryption and decryption operations. To encrypt a message M, the sender computes the ciphertext C by raising the message to the power of the public exponent E modulo n. Formally, the encryption of M is M to the E mod n. To decrypt this ciphertext and recover the original message, the receiver uses their private exponent D. The decryption of C is C to the D mod n. The security of this entire mechanism rests on the fact that while n and e are public, d cannot be calculated without knowing phi of n, which in turn requires knowing the prime factors p and q. Thus, an attacker's only path to breaking the system is to factor the large modulus n, a task that remains computationally infeasible for modern computers when the primes are sufficiently large. The fundamental question at the heart of RSA is why the decryption process successfully recovers the original message. Specifically, we must prove that raising a ciphertext to the power of the private exponent d, which is equivalent to raising the original message m to the power of the product e times d, returns us to the original message m modulo n. To establish this proof of RSA correctness, we rely on two pillars of number theory, Fermat's little theorem and the Chinese remainder theorem. The strategy is elegant. Rather than tackling the composite modulus n directly, we break the problem down into its prime components, p and q. Because n is the product of these two distinct primes, any congruence that holds modulo p and modulo q simultaneously must also hold modulo their product, n. This reduction is the key insight that makes the proof manageable. To begin, we recall the definition of our encryption and decryption keys. The exponents e and d are chosen such that their product is congruent to 1 modulo the totient of n, which for a product of two primes is p minus 1 times q minus 1. Mathematically, this means there exists some positive integer k such that the product e times d equals 1 plus k times p minus 1 times q minus 1. This specific structure of the exponent is what allows us to invoke Fermat's little theorem later in the derivation. Our goal is to show that m raised to the power of e times d is congruent to m modulo p. We must consider two distinct scenarios for the message m in relation to the prime p. In the first case, we assume that p divides m. If m is a multiple of p, then m is congruent to 0 modulo p. Consequently, any positive power of m, including m raised to the power of e times d, will also be congruent to 0 modulo p. Thus, the identity holds trivially. 0 is congruent to 0. This covers the edge case where the message shares a factor with the modulus. The second, more common case is when p does not divide m. This condition is required to apply the standard form of Fermat's little theorem, which states that for any integer a not divisible by p, a raised to the power of p minus 1 is congruent to 1 modulo p. We start our derivation by substituting our expression for the exponent e times d. Step 1. We write m raised to the power of e times d as m raised to the power of 1 plus k times p minus 1 times q minus 1. Step 2. Using the laws of exponents, we decompose this into m times m raised to the power of k times p minus 1 times q minus 1. Step 3. We further rearrange the second term to isolate the Fermat-friendly component, writing it as m times the quantity m raised to the power of p minus 1, all raised to the power of k times q minus 1. Step 4. We invoke Fermat's little theorem. Since m is not divisible by p, the inner term m raised to the power of p minus 1 is exactly 1 modulo p. This simplifies our expression to m times 1 raised to the power of k times q minus 1. Step 5. Because 1 raised to any power is 1, we are left with m times 1, which is simply m. This completes the proof that m raised to the power of e times d is congruent to m modulo p. Due to the perfect symmetry of the RSA setup, we can repeat this exact logical sequence for the other prime factor, q. By simply interchanging the roles of p and q in the derivation, we prove that m raised to the power of e times d is also congruent to m modulo q. Now we have two simultaneous congruences. The expression is congruent to m modulo p, and it is congruent to m modulo q. Because p and q are distinct primes, they are coprime. The Chinese remainder theorem tells us that if a number satisfies these two conditions, it must also satisfy the congruence modulo their product, p times q. Therefore, we conclude that m raised to the power of e times d is congruent to m modulo n. This mathematical certainty ensures that the decryption process is the functional inverse of encryption, allowing the original message to be recovered perfectly every time. To ground our theoretical understanding of RSA, we will walk through a concrete numerical example using small primes. While real-world RSA implementations utilize primes with hundreds of digits to ensure security, the underlying mathematical mechanics remain identical at this tiny scale, making the process much easier to visualize. Consider a scenario where Bob wants to receive a secure message from Alice. He must first set up his cryptographic parameters. Bob begins the key generation process by choosing two prime numbers. In this example, he selects p equals 3 and q equals 11. The first step is to calculate the modulus n, which is the product of these two primes. Thus, n equals 3 times 11, which gives us 33. This value of 33 is public. It will be used as the base for all modular arithmetic in the exchange and defines the range for our possible messages. Next, Bob must calculate Euler's totient function, phi of n. For a product of two primes, this is calculated as p minus 1 multiplied by q minus 1. Here, that is 2 times 10, resulting in 20. This value is never shared publicly. It is essential for the next step of key generation because it determines the cycle of exponents in our modular system. Now, Bob needs to choose a public exponent. The requirement for E is that it must be relatively prime to phi of n, meaning it shares no common factors with 20 other than 1. Bob looks at the factors of 20, which are 2, 4, 5, and 10, and chooses E equals 3. Since the greatest common divisor of 3 and 20 is 1, this is a valid choice. The final part of Bob's setup is calculating his private key, D. This value d is the modular multiplicative inverse of e modulo phi of n. We need to find an integer d such that 3 times d is congruent to 1 modulo 20. We can find this by testing multiples of the modulus plus 1. Looking at 20 times 1 plus 1, we get 21. Since 21 is exactly divisible by 3, we find that d equals 7. Bob now has his full key pair, a public key composed of the pair 33 and 3, and a private key d equals 7, which he keeps secret. Bob transmits the public key parameters n equals 33 and e equals 3 to Alice. Alice now has a message she wishes to send. The integer m equals 4. It is important to note that the message must be an integer between 0 and n-1, so 4 is well within the valid range. To encrypt this message, Alice performs a modular exponentiation using Bob's public key. She calculates the ciphertext C by raising the message m to the power of e, then taking the result modulo n. Specifically, she computes 4 cubed modulo 33. Let's calculate that step by step. 4 cubed is 4 times 4 times 4, which equals 64. Now we perform the modular reduction. We divide 64 by 33 and find that it goes in once with a remainder. 64 minus 33 equals 31. Therefore, the ciphertext C is 31. Alice sends this value across the insecure channel to Bob. Upon receiving the ciphertext 31, Bob uses his private key D equals 7 to decrypt it. He performs a symmetrical exponentiation operation. The message m is recovered by raising the ciphertext C to the power of D modulo n. This requires Bob to calculate 31 to the power of 7 modulo 33. Calculating 31 to the 7th power directly would result in a very large number, but modular arithmetic allows us to simplify the process significantly. Since we are working modulo 33, we can replace 31 with its smaller negative representative, -2, because 31 is 2 less than 33. This transforms our problem into calculating -2 to the 7th power modulo 33. -2 raised to the 7th power is -128. To find where this sits in our modular system, we add multiples of 33 until we reach a positive value. 33 times 4 is 132. Adding 132 to -128 gives us exactly 4. Through this process, Bob has successfully recovered the original message, m equals 4. This walkthrough demonstrates that the encryption and decryption operations are mathematically symmetrical. The cycle from 4 to 31 and back to 4 is guaranteed by the relationship between the exponents e and d and the modulus. While an observer might see the numbers 33, 3, and 31, they cannot easily reverse the encryption to find the message 4 without knowing the private key d, which is protected by the difficulty of factoring 33 back into its prime components. The RSA cryptosystem provides a powerful mechanism for confidentiality, but its mathematical structure offers a second, equally vital capability, the digital signature. While encryption ensures that only the intended recipient can read a message, a digital signature ensures that the recipient can verify exactly who sent the message and that the content has not been altered. The key insight behind the RSA signature protocol is a symmetry in the mathematics. The roles of the public and private keys are effectively reversed compared to the standard encryption process. In the standard encryption flow, a sender uses the recipient's public key to hide a message. With signatures, the sender uses their own private key to sign the message. Because the private key is known only to the owner, the resulting signature serves as a unique mathematical thumbprint that no one else could have produced. Consider the scenario where Bob wants to send a signed message M to Alice. Bob already possesses his RSA key pair, a public key consisting of the modulus n and the exponent e, and a private key d. We assume the message m is an integer between 1 and n-1. To create the signature, Bob performs a modular exponentiation using his private key. He calculates the signature s by raising the message m to the power of his private key d modulo n. Formally, this is written as s equals m to the power of d mod n. Because Bob is the only person who knows the value of d, he is the only person capable of performing this specific calculation. Once the signature s is generated, Bob sends both the original message m and the signature s to Alice as a pair. When Alice receives this pair, she needs to verify that Bob was indeed the author. To do this, she uses Bob's publicly available key, e and n. She performs the inverse operation. She raises the signature s to the power of Bob's public exponent e modulo n. Let's call the result of this calculation m prime. If the resulting m prime is exactly equal to the original message m, Alice has mathematical proof of two things. First, the message is authentic. It must have been signed by someone possessing the private key d corresponding to the public key e. Second, the message has integrity. If even a single bit of the message M or the signature S had been changed during transmission, the modular exponentiation would have yielded a completely different result, and the equality would fail. To see this in action with concrete numbers, let's use the parameters from our previous example where p equals 3 and q equals 11, giving us a modulus n of 33. We calculated phi of n as 20, chose a public exponent e of 3, and found the private key d to be 7. Suppose Bob wants to sign the message m equals 4. In the first computational step, Bob generates the signature. He calculates s equals 4 to the power of 7 mod 33. To break this down, 4 squared is 16, and 4 to the power of 4 is 16 squared, which is 256. Since 256 divided by 33 is 7 with a remainder of 25, we have 4 to the power of 4 congruent to 25 mod 33. Then, 4 to the power of 7 is 4 to the power of 4 times 4 squared times 4, which is 25 times 16 times 4, equaling 1600. Dividing 1600 by 33 gives 48 with a remainder of 16. Thus, Bob's signature S is 16. In the second step, Alice receives the message 4 and the signature 16 and begins verification. She calculates m prime equals 16 to the power of 3 mod 33. First, she finds 16 squared, which is 256. As we saw, 256 mod 33 is 25. In the third step, she completes the calculation. 16 cubed is 25 times 16, which is 400. To find 400 mod 33, she divides 400 by 33, which goes 12 times with a remainder of 4. Since her calculated m prime of 4 matches the received message m of 4, the signature is verified as valid. The mathematical correctness of this process relies on the same identity we used for RSA encryption. The verification step computes s to the power of e, which is m to the power of d raised to the power of e. This simplifies to m to the power of d times e mod n. Because d and e are modular inverses of each other modulo phi of n, the product d times e is congruent to 1 mod phi of n. As we proved earlier using Fermat's little theorem and the Chinese remainder theorem, raising any integer m to a power that is 1 mod phi of n results back in m, provided we are working modulo n. This confirms that the verification process will always recover the original message if the signature is legitimate. This protocol fundamentally changes the nature of the keys. In encryption, the public key is for writing and the private key is for reading. In signatures, the private key is for writing the signature and the public key is for reading and verifying it. This ensures that while anyone can verify a signature, only the rightful owner of the private key can create one, providing a robust foundation for trust in digital communications. The fundamental paradox of cryptography is how two individuals who have never met and share no prior secrets can establish a secure, private communication channel while an adversary monitors every word they say. This challenge is addressed by the Diffie-Hellman Key Exchange, a landmark public key protocol that revolutionized the field by allowing the creation of a shared secret over an insecure medium. Unlike RSA, which we used for direct encryption and digital signatures, Diffie-Hellman is specifically designed for key agreement. To begin, the participants, Alice and Bob, must agree on two public parameters. The first is a very large prime number, denoted as p. The second is an element alpha, which belongs to the set of integers modulo p, specifically the multiplicative group zp star. These two values, p and alpha, are public. Anyone, including a passive eavesdropper named Eve, can see them. With these parameters established, the protocol proceeds in 3 distinct computational phases. In the first phase, Alice and Bob generate their private contributions. Alice chooses a secret integer, little a, typically from the range of 2 to p minus 2. This value remains strictly on her machine. She never shares it. She then performs a modular exponentiation to calculate her public value, a. Specifically, she computes a equals alpha raised to the power of a modulo p. Simultaneously, Bob chooses his own secret integer, little b, from the same range. Just like Alice, he keeps b private and computes his public value, b, by calculating alpha raised to the power of b modulo p. At this point, Alice holds the pair A and A, while Bob holds B and B. In the second phase, the exchange occurs. Alice sends her public value A to Bob, and Bob sends his public value B to Alice. It is crucial to note that while A and B are traveling across the network, an eavesdropper only sees these results of exponentiation, not the secret exponents A and B themselves. The shared secret is never transmitted directly. In the final phase, both parties derive the common key, K. Alice receives B from Bob and uses her private exponent A to compute K equals B raised to the power of A modulo P. Bob receives A from Alice and uses his private exponent B to compute a value K prime, which is A raised to the power of B modulo P. Although they performed different calculations using different private inputs, the laws of modular arithmetic ensure they arrive at the exact same result. We can see why by substituting the original definitions of A and B back into these final equations. Alice's calculation of B to the A is equivalent to taking alpha to the B and then raising that to the A, which simplifies to alpha to the power of BA. Conversely, Bob's calculation of A to the B is equivalent to taking alpha to the A and raising that to the B, which simplifies to alpha to the power of AB. Because multiplication in the exponent is commutative, meaning AB equals BA, the final results K and K prime are identical. They now share a secret value, alpha to the AB mod P, which can be used as a key for symmetric encryption. This entire process relies on the commutativity of exponentiation, allowing two independent paths to converge on a single hidden mathematical destination. The security of the Diffie-Hellman protocol rests on a fundamental asymmetry in modular arithmetic. While it is computationally efficient to raise a number to a power, reversing that process is extraordinarily difficult. Consider an adversary, often referred to as Eve, who is passively monitoring the communication between Alice and Bob. Eve sees the public parameters, the prime P and the base alpha, and she intercepts the public keys A and B. To compromise the communication, Eve must find the shared secret, K, which we know is alpha raised to the product of the private exponents A and B modulo P. This specific challenge, calculating alpha to the power of AB from alpha to the A and alpha to the B, is formally known as the Diffie-Hellman problem. However, the most direct way for Eve to solve this is to solve the discrete logarithm problem instead. If she can determine the private exponent A from the public value A, the protocol's security collapses. This exponent x is called the discrete logarithm of beta to the base alpha. While the term logarithm suggests a relationship similar to standard calculus, the discrete version lacks the smooth, continuous properties that allow for easy calculation in the real numbers. In modular arithmetic, the values of alpha to the x jump around the set of remainders in a seemingly random, chaotic fashion, providing no clear path for an adversary to zero in on the correct exponent. This makes modular exponentiation of one-wave function easy to compute in one direction, but practically impossible to invert. For the Diffie-Hellman protocol to be truly secure, the discrete logarithm problem must remain computationally infeasible for any attacker. This difficulty is not guaranteed by the math alone. It depends heavily on the choice of parameters. There are three essential conditions that must be met. First, the prime number P must be very large, typically 2048 bits or more in modern systems. If P is too small, an attacker can simply use brute force or exhaustive search, testing every possible value of x until a match is found. Specifically, the smallest positive integer m, such that alpha to the power of m is congruent to 1 modulo P, should be a large value. If alpha generates only a small subgroup of the possible remainders, the search space for the attacker is significantly reduced, making the problem trivial. Finally, the value p-1 must possess at least one large prime factor. This requirement is necessary to defend against specialized attacks like the Polig-Hellman algorithm, which can break the discrete logarithm problem by decomposing it into smaller, easier problems if p-1 is composed entirely of small prime factors. By ensuring these three conditions are satisfied, we create a mathematical environment where calculating the shared secret is so time-consuming that it becomes effectively impossible, even for the world's most powerful computers. While the discrete logarithm problem is computationally hard in general, its security relies entirely on the specific choice of the base alpha. To see why, consider a prime p equal to 5896, 405, 408, 99, 04, 1833, 683, 9907. Suppose we choose a base alpha equal to 1513, 693, 380, 770, 2966, 151, 374, 84, and we are given a target value beta equal to 4382, 2712, 02, 3287, 4518, 164, 0232. At first glance, finding the exponent a such that beta equals alpha to the power of a modulo p seems daunting given the scale of these numbers. However, a quick check reveals that alpha cubed is congruent to 1 modulo p. This implies that the powers of alpha cycle through only 3 distinct values: alpha to the 0, alpha to the 1, and alpha squared. Since beta is not 1 and beta is not alpha, we immediately know that a must be 2. This vulnerability occurs because the order of alpha is far too small. Formally, we define the order of an element a in a group as the smallest positive integer k such that a raised to the power of k equals the identity element, which is 1 in our multiplicative group. In the finite group Zp star, every element has an order that must divide the cardinal of the group, which is p minus 1. To maximize security, we seek a primitive element, also known as a generator. A primitive element is one whose order is exactly p minus 1, meaning its powers generate every single non-zero remainder in the field. Using a primitive element ensures that the cycle is as large as possible, forcing an attacker to search through the entire key space. To verify if an element alpha is primitive without computing every power, we use a specific theorem. For a prime p, alpha is a primitive element if, for every prime divisor q of p minus 1, alpha raised to the power of p minus 1 divided by q is not congruent to 1 modulo p. This provides an efficient algorithm. We factor p minus 1, pick a candidate alpha, and perform these modular exponentiations. If all results are different from 1, alpha is a generator. Since Zp star is a cyclic group, generators are abundant, and we are guaranteed to find one after just a few random trials, establishing a secure foundation for the Diffie-Hellman exchange.